Okay, so we're going to finish up Calc 1.4. This is the second part of that lesson, and it's a little bit shorter than the first. And we're going to start with properties of continuity. So this is not a new concept for you guys. Hopefully you'll feel pretty comfortable with this stuff. But the properties of continuity when it comes to two functions that we know are already continuous at a certain point means that any operation of those two continuous functions are going to also be continuous. So you can combine them using different operations and the result is still continuous. So in terms of what functions we've seen that we know are continuous, we've studied lots of continuous functions. So I mean, you could think back to the basics when you started several years ago in high school, at least. Linear function, those are continuous on the entire domain. Quadratic functions, most polynomials, and lots of trig functions as well. So we know sine of x, we know cosine of x is continuous. So we've seen a lot of continuous functions that are continuous over their entire domain. So when we're asked something like over what domain are the following functions continuous, so at first glance, some of these functions might seem a little complicated to know whether or not they're continuous. But if you break it down from these properties we saw above, if we can at least identify two separate functions and we know that each of the separate functions are continuous, then we can break down the continuity of the combined function. So in number 1, we've got f of x equals 3 raised to the x. So if we think about 3 raised to the x, we can plug in any value of x we want, and that function is defined. So that means 3 to the x is continuous over its entire domain. And 4x squared, we know we can square any number. We can multiply any number by 4. So this second piece is also continuous over all of the real numbers, which means their product is also continuous over the real numbers. So number 1 has the domain negative infinity to infinity, and it's continuous over that full domain. Okay, so number 2, we have f of x equals the log of x minus the square root of x. So if we want to know over what domain that entire function is continuous, we can break it down into these two functions. Hopefully you remember from logs that we cannot take the log of a negative number, nor can we evaluate log of 0. It just isn't possible. It doesn't make sense. So this part of it is continuous starting at 0 and continuing to infinity. And then for the square root function, so we know this function is defined for any number as long as it's not negative. So we know its domain is including 0 and infinity to infinity. So when we're talking about the domain of the entire function of those two combined functions, we would need to take the more restrictive domain, which is 0 to infinity not including 0, because it needs to work for both pieces of that. So number 2 has so we would combine both of these and we would have 0 to infinity, not including 0. In number 3, we see a few different functions as well. We see the sine of 3x, 2x squared, and negative 4 to the x. So each of these 3 individual functions are all continuous over the entire set of real numbers. So their combination is also continuous from negative infinity to infinity. And then lastly, we see cosine squared of x divided by x squared plus 1. So again, we want to break this into the two. So cosine squared of x, that is continuous. So it's just the cosine function squared. You can take the cosine of any real number. So when you square that, again, it applies to all real numbers. So that has a domain of all real numbers. This function having a fraction should raise a red flag for you because we cannot divide by 0. However, no matter what, the only way that this denominator could equal 0, if you think about it, since it's x squared plus 1, that would mean x squared, when you add 1 to it, in order for that whole thing to equal 0, that would mean x squared would have to end up equaling -1, since when you add 1, it would equal 0. And when you take the square root of that, that would mean x would have to be a non-real number. So this is limited to the real number system. So this denominator also has a domain of all real numbers. So while at first glance you see the fraction and you're expecting restrictions, number 4 also has a domain of -infinity to infinity, because that denominator is never going to equal 0. Okay, so this next section refers to continuity of composite functions. So again, a lot of this is review from first semester. So we did already talk about continuity of composite functions. We're just revisiting it in this section since it's all about continuity. So composite functions, remember, is taking one entire function and plugging it into the other. So we see this notation here. That indicates you've taken the inside function g of x and you've actually plugged that into the function f. And what we know is that if the inside function, so in this case g, if g is continuous at c and f is continuous at g of c, since that's what you're plugging into f, then the composite function is also continuous at c. So if we look at this first example here, describe the intervals where f of g of x is continuous. The important thing here is that the composite function, if it's not continuous at this inside function at a certain value, then the whole composite function isn't going to work either. So you really need to think about that inside function, the domain of that. So x minus 1, when you take the square root of that, x cannot be any less than 1, otherwise you would get non-real values. So in this first example, the interior function has a limit. The exterior function, sine of x, that we're taking g of x and plugging into, as long as that's a real number, sine of x is defined over all real numbers. So the composite function f of g of x has the restriction that x has to be greater than 1, so that domain is 1 to infinity. And then for number 5, we see our two separate functions. We see the absolute value of x, and then the inside function is 1 plus cosine of x. So again, when we're dealing with composite functions, that inside function is the one we care about. You can take the absolute value of any real number, and this is conveniently, cosine of x is defined over all real numbers as well. So their composite function is also defined over all reals. So that would be -infinity to infinity. All right, so just determining the values where a function is not continuous. Again, we're looking for those values where the function is not defined for any reason. So in number 7, it's pretty clear just at first glance that this function is discontinuous when the denominator equals 0. So there's a discontinuity here at -1, and that's it. So we're just asked to determine where it's not continuous. So again, more review. For the second one, it's kind of a review of what we saw in the first part of these notes, where with a piecewise function, you can't assume it's discontinuous just because you see this break in the function or this change of graph or change of behavior in the function. So we definitely know that this entire step function changes at 1, but if it's continuous or not, we have to do a little bit of work. So the two pieces of work we need to do are figure out what the function equals when you plug 1 into this first function, and then when we plug 1 into the second piece. And if their output is the same, then it's a smooth transition from one piece of the graph to the second piece. So when we plug 1 into x squared plus 1, you get 1 squared plus 1, which is 2. When we plug 1 into the second half, it would be the square root of 3 plus 1, which is the square root of 4, which is also 2. So what that means is, because even at the two separate pieces of this function, they have the same y value, so it's a smooth switch from the one to the other, from this one defined piece to this defined piece, which means this function is actually continuous over the entire real number system. So continuous over So this is continuous over the reals, which may confuse some of you because this piece does have a restriction. However, we're only using this part of the function for when x is greater than 1. And there's the restriction on this begins at -3 for x. So that means if x is less than 1, we're actually squaring x and then adding 1. So the piecewise function, based on this domain and the two different ones, continuous over all reals. Okay, let's take a look at the last page. All right, so again, we're looking for any values where the function is not continuous. So again, just because we see piecewise doesn't mean we can immediately assume that it is discontinuous at this change in the graph. So we need to think about what's happening in the function at that x value of 0. So in this case, if x does equal 0, the value of the function is 0 itself. If x does not equal 0, we're using this. So we know the y value for this second piece of the function is 0, so we would need to see the y value for this piece of the function when x equals 0. However, we can't even plug 0 into that first piece of the function. So what that means is there is an essential discontinuity at 0 because of this, the fact that this first piece of the function is undefined at 0. So this is defined, or this is undefined, so we've got an essential discontinuity at x equals 0 in number 9. All right, number 10 is pretty similar. We're actually going to jump to example 11 here. Number 11, again, we see the piecewise function. We see that the graph, the function changes when x equals 5. So we need to know now what is happening at 5 in both of these functions. In the top function, when we plug 5 in, we would get 15 minus 1, which is 14. In the second function, when we plug 5 in, we would get 25, so 5 squared, minus 2 times 5, 10, minus 2 more. So 25 minus 10 minus 2 is 13. So because this function, when it changes from the first piece to the second piece, it equals two different y values for 5 at both in both of those functions, which means this has a discontinuity, specifically an essential one, at x equals 5. Okay, in these last 3 examples, I love this type of problem because it's just kind of like a puzzle, and you all know I love puzzles. Okay, so in these problems, it's asking you to find the constant a or b that would make these functions continuous. So if you look at number 12, we see a piecewise function that's not fully defined. We see this little a here. We know that there's a change in the graph when x equals 2, so it's defined in x to some power when x is less than or equal to 2, and then it's 10 minus x, this linear function, when x is greater than 2. Now, if we want this function to be continuous, x raised to a power is always continuous for any value of x. 10 minus x is also continuous for any value of x. But if this is a piecewise function, we want it to be a smooth transition, meaning we want the y value for this function where it leaves off at 2 to be exactly the same y value for the second function where it picks up at 2. So how would we figure out what that value of a has to be? So since we already know what the exact function is for the second piece of this, we know what this second function is going to do at 2. Because if we plug 2 in here, it would just be 10 minus 2. So the second one has a f of 2 equals 8. So if this function had a smooth transition from first to second piece, then we would want this to also equal, we would want x to the a equal to 8 when x equals 2. So now we need to think about 2 to what power equals 8. So then we know that if a equals 3, if this is x cubed, then this piecewise function will be continuous because they'll have the same y value at 2 on each different piece of the function. So when we look at number 13, it's very similar. So we've got two pieces to the function, and we want it to be continuous. So again, the change in the graph happens when x equals 1. So for everything up to and equal to 1, we're following this rule, x squared minus 4. And then after 1, we're following ax plus 5. Again, for a smooth transition, for a continuous transition from this function to the second function, we want their y values to be identical when x equals 1. So since the top half of that function is already defined, we can figure out what the function is at 1 there. So it would be 1 squared minus 4, which is negative 3. What that means is we want this whole thing to equal negative 3 when x equals 1. So that means we just plug 1 in to the second rule. So a times 1 plus 5. And then we can just solve for a, and that will make this second piece have a y value as the same as the first piece when x equals 1. So we can just quickly subtract 5 from both sides, and we get negative 8 equals a. And then you can do a quick check. It should make sense. So when you go back up and re-examine this, plugging, visualizing a negative 8 out front, plugging 1 in, negative 8 times 1 is negative 8 plus 5 is negative 3, which means it would be a smooth transition from this piece to that second piece. All right, this last problem, number 14, is another piecewise function, but this one will be a little more challenging because it has 3 pieces and it's got 2 unknown variables. So we know that the first piece here, the function is just 3 itself. So the graph of this piecewise function, it is a horizontal line. As long as x is less than or equal to 2, it's just a horizontal line at 3. As long as x is greater than or equal to 4, we've got another horizontal line at negative 3. So if you think about, I'm going to draw a quick sketch just so you guys... Alright, so 1, 2, 3, 1, 2, 3. And then the switches here, the change in the graph happen at x equals 2. And then we see here the 2 and the 4. Let me use my pointer. So at 2, the graph changes to this linear graph, ax minus b. And then it's that linear graph up to 4. And then at 4, it changes again to negative 3. So that means, if I'm doing a quick sketch here, so we've got a horizontal line at 3 up to 2. So x is 2, y is 3. We've got that. At 4, 1, 2, 3, 4, we pick up again at negative 3. So in between this is this missing piece of our piecewise function, and we need to figure out the a and the b there. So you guys know enough about linear functions that basically what we're looking for is the slope and y-intercept of that small chunk of a line that's going to connect the 2 horizontal lines, because the question is asking find a and b so that the entire piecewise function is continuous over the set of reals. So the graph hopefully is giving you a visual. You can go old school and you basically know 2 points on this graph. You know that this point right here is 2, 3, because you're told that in the definition of the function. At 2, that line has the point 2, 3. That line also has the point 4, negative 3. So we have 2 points on a line. That's enough to tell you slope and y-intercept using methods you guys learned several years ago. So let's just finish the problem doing that, and then I'm going to show you a second way that you can think about this. So basically what I've concluded here is I know I've got the point 2, 3 on my line, and I've also got the point 4, negative 3 on my line, which comes from just how the first and last piece of this piecewise function is defined. From those 2 values, I can calculate the slope of that line. We know slope as the change in y over the change in x. So I'm going to start with this point, and my change in y will be negative 3 minus 3. So that would be negative 6. And the change in x is 4 minus 2, which is 2. So this gives me a slope of negative 3. So before we move on, let's just make sure that makes sense. Clearly our line has a negative slope. So that should work. And then how does that get me closer? Well, I know I have negative 3x plus b now that I know the slope, and I have 2 points on my line, so I can use those, either one of these points, to plug in for x and y, and then I can solve for b. So let's use our first point of 2, 3. So that would be 3 equals negative 3 times 2 plus b, or 3 equals negative 6 plus b. Add 3 to both sides, and we get that b equals 9. So we already knew that the a equals 9. And then when we solve for b, I'm just going to confuse all of you, I have a feeling. So we know that in our equation y equals mx plus b, that this b would be 9. However, if you look at the way our function is defined, it's ax minus b. So if we got a positive 9 here to plug in for plus b, then the solution to our problem, which is ax minus b, b would equal negative 9. So the solution to this problem is a equals negative 3, b equals negative 9. And if you're not convinced, I will show you another way to think of it. So I might run out of space. That's fine. Okay. I'm just going to leave it like that. So I'm going to use this other space over here to show you guys another way to think of this. Although it's not really a different way. I mean, I'm calling it a different way, but you'll see it's kind of the same as that first process, but it's set up a little different, and that would be in a system of equations. So if I want to represent this situation with a system of equations, what we have to go back and realize is we want this middle function to, in order to be continuous, for the whole thing to be continuous, we want this middle piece to have the same y value as the first piece. So we want it to have a y value of 3, so I'm going to set it equal to 3 when x equals 2. So when I plug 2 in for x here, I want that whole middle piece to equal 3. So that would be a times 2 minus b. So here's my first piece of the system. My second equation in the system will come from the fact that I want this exact same ax minus b to equal negative 3 when x equals 4. So that would give me the setup. I want it to equal negative 3, so a, when the x equals 4 minus b. So we see it's very similar to what we did here, it just looks different. So I'm setting what we want up to positive 3 when x equals 2, negative 3 when x equals 4, and then I need to figure out what a and b are going to be in order to make this system true. So what we have here, if you remember doing systems of equations using the elimination method, which is what I would use here, the elimination method is to get it set up in a way that when you combine by adding all the terms straight down, one of the terms, either a or b, is gone. Is eliminated. So we see here the negative b and negative b. If I add these up together right now, that would be negative 2b. However, if I just made this simple change of negating this whole second function and multiplying it by a negative 1, that would make this a positive 3, this would make this a negative 4a, and that would make that negative b a positive b. So when I add them together, I get 3 plus 3, which is 6. I get 2a minus 4a, which is negative 2a, and then the b's are gone because they've been eliminated. Now I can simply divide by negative 2 to get my a value of negative 3, which is consistent with the negative 3 that we solved for by way of using the slope formula in the first method. And then to finish off my second method here, all I would have to do is solve for b, but since I know that a is negative 3, I could just pick one of these equations and plug -3 into it. So that would give me, I'm going to plug it back into this first equation. So it would be 3 equals -3 times 2, which is -6, minus b. And then I would add 6 to both sides, and I would get 9 equals -b, which means b equals -9, which is consistent with the value of b we got down here. So there's two ways you can think of it. You can kind of go back to revert back to, okay, I have 2 points, I know how to calculate slope, substitute in to solve for b, or you can set up the system of equations with your 2 equations and solve that way. Hopefully that's all making sense to you guys. I think there's at least 1, maybe 2 of these in the homework, so you'll definitely get a chance to practice that process. All right, and then this last chunk of notes here is on the intermediate value theorem, which hopefully sounds familiar because we did this during first semester as well. Because this is already a super long section, I'm going to skip this review of the intermediate value theorem, not because it's not important, but because we've seen this before. So you can read through it, but I will not include intermediate value theorem moving forward on homework or assessments, just because, again, this is something you guys have seen, and I just want to keep us moving. All right, so that's it on Calc 1.4. You should be good to go to finish the homework assignment, and then we'll move on to 1.5 next time.